All right, fellow curious creatures, and welcome back to Shadow Deaf Life. Today, we're not just tinkering in the garage. We're diving headfirst into the annals of history, into the labs, and sometimes even under the bleachers of football stadiums to uncover the moments that made our modern world. All right, let's get those lab coats on and dive into some mind-blowing science that utterly changed the game. We're talking about experiments so audacious, so out there, that they completely rewrote what we thought we knew about, well, everything. These are the stories of scientists who looked at the universe and said, I wonder what happens if I try this. And lucky for us, they did. Welcome back to Shadow Deaf Life, where we're about to count down the 10 craziest science experiments that changed the world. We're going to explore the kind of science that makes you lean back in your chair and go, no way they actually did that. From peering into the very code of life itself, to literally splitting atoms with less safety gear than I use for a glitter bomb. These experiments are the bedrock of our understanding. We'll see moments of sheer genius, a few happy accidents, because science is messy sometimes, and a whole lot of perseverance. These scientists weren't afraid to ask the big questions, even if the answers were totally unexpected. So, buckle up, because this is going to be a wild ride through scientific history. Get ready for some serious whoa moments, a dash of oops, and a whole lot of thank goodness they did that. We're celebrating the bold, the brilliant, and the occasionally bonkers pioneers who dared to experiment and, in doing so, gifted us with the knowledge that shapes our lives every single day. Don't forget to hit that like button, subscribe if you haven't already, and let's get weird. This is going to be epic, folks. Prepare for your brain to get a little bit bigger today. All right, kicking off our list at number 10, we have something truly monumental, the Human Genome Project. Imagine trying to read the entire instruction manual for a human being. Not just one chapter, like how to build an eyeball, but the whole thing. All 3 billion letters of our DNA. That's what these scientists decided to do. It was like deciding to hand copy the entire internet, but with even tinier font and way more at stake. This wasn't one person in a lab coat. This was a massive, global collaboration. A scientific Avengers team up, racing against the clock, and sometimes each other. The sheer scale is mind-boggling. They were literally mapping out the blueprint of what makes us, us. The challenges they faced were insane. Think about it. The technology to do this efficiently didn't even fully exist when they started. They were building the plane while flying it, developing new sequencing techniques, new computer programs to handle the mountains of data. It was an engineering feat, as much as a biological one. And the data, imagine spreadsheets that stretched to the moon and back. They had to figure out not just what the letters were, but what they meant. It's like being given a giant book in an alien language, and your job is to translate it and then write a user guide. The pressure was immense, and the potential for error was huge. But the drive to understand our own genetic code was even bigger. And when they finally did it, when that first draft of the human genome was published, game changer. It was a profound, know thyself moment for humanity. Suddenly, we had this incredible map that revolutionized medicine, leading to new ways to diagnose, treat, and even prevent diseases. We started understanding the genetic basis for so many conditions, from cancer to cystic fibrosis. It opened up entirely new fields like personalized medicine, where treatments can be tailored to your specific genetic makeup. It's like going from a blurry old TV signal to stunning 4K Ultra HD for understanding human biology. This project didn't just change science, it changed our relationship with ourselves. Coming in at number 9 is an experiment that literally happened in secret, under the bleachers of a squash court at the University of Chicago. We're talking about Enrico Fermi and his team building the world's first artificial, self-sustaining nuclear chain reaction with Chicago Pile 1. Picture this. It's 1942. World War II is raging, and these scientists are stacking graphite bricks and uranium lumps, essentially building a nuclear reactor in the middle of a bustling city, with no radiation shielding to speak of, and a safety system that basically involved a guy with an axe ready to cut a rope. The safety control Rod Axeman, or Scram. If that's not crazy, I don't know what is. The stakes were astronomically high. They were venturing into completely uncharted territory. What if they miscalculated? What if the reaction ran away from them? They were literally teasing the atomic dragon's tail. Fermi, cool as a cucumber, directed the slow withdrawal of the cadmium control rods. The Geiger counters clicked faster and faster. The tension in that room must have been thicker than my mom's gravy. They knew that if this worked, it would unlock a power source, unlike anything humanity had ever seen, but it also held the potential for unimaginable destruction. It was a knife-edge moment, a true scientific gamble with the fate of the world potentially hanging in the balance. And then, it happened. The chain reaction became self-sustaining. For 28 minutes, humanity controlled nuclear fission for the first time. While it directly led to the atomic bomb, which is a terrifying and somber part of its legacy, this experiment also paved the way for nuclear power plants that now generate a significant chunk of the world's electricity. It was a Pandora's box moment for sure, but the sheer audacity of building a nuclear pile under a football stadium with such rudimentary controls and pulling it off, that's pure, high-stakes, world-changing science. It's like they were playing Jenga with radioactive bricks, and the world held its breath. Number 8 takes us back to the 18th century, to a guy named Antoine Lavoisier, who basically said, "Hold my powdered wig. I'm about to invent modern chemistry." Before Lavoisier, people believed in this weird mystical substance called phlogiston. The idea was that flammable things contained phlogiston, and when they burned, they released it. It sounds a bit like saying your car runs on Zoom Zoom juice, and when it's empty, the juice is just gone. Lavoisier, being a meticulous kind of dude, wasn't buying it. He was obsessed with weighing things, before, during, and after reactions. He was the original spreadsheet king of the chemistry lab. So, Lavoisier started conducting these super careful experiments, especially with combustion. He'd burn stuff like phosphorus and sulfur in sealed containers, and he noticed something crucial. The ash or product weighed more than the original substance. If phlogiston was being released, shouldn't it weigh less? This was a major head-scratcher for the phlogiston fans. Lavoisier figured out that the burning material was actually combining with a part of the air, which he later named oxygen. He showed that when you account for all the substances involved, including the gases, mass is neither created nor destroyed. This became the law of conservation of mass, a cornerstone of all chemistry. It's hard to overstate how revolutionary this was. Lavoisier dragged chemistry out of the realm of quasi-magical thinking and into the world of precise, quantitative science. He wasn't just mixing potions. He was measuring, calculating, and proving. Imagine trying to bake a cake if you didn't know that ingredients have to add up. Sometimes it's a cake, sometimes it's a brick, sometimes it just vanishes. That was chemistry before Lavoisier. He gave us the fundamental grammar for understanding chemical reactions, proving that matter doesn't just poof in and out of existence. Thanks to his obsession with his fancy scales, we can actually understand what's happening at a chemical level. All right, for number 7, we're celebrating the patron saint of messy scientists, Alexander Fleming, and his accidental discovery of penicillin. This is one of those classic oops, I just changed the world moments. So, Fleming wasn't exactly known for his tidy lab. Legend has it, he went on vacation in 1928 and left a stack of petri dishes growing bacteria by an open window. When he got back, instead of just chucking the contaminated plates like a normal, less genius person might, he actually had them. He was basically the Sherlock Holmes of forgotten lab experiments, always noticing the little details. And what did he notice? One dish had this weird mold growing on it, a penicillium mold, probably floated in from a breadcrumb or something. But here's the crazy part. Around the mold, the bacteria were, totally wiped out. It was as if the mold had put up a "no bacteria allowed" sign. Most people would probably just grumble about contamination and start over. But Fleming thought, that's interesting. That moment is where the magic happens, in science, folks. He realized this mold was producing something that was actively killing the bacteria. He called it mold juice initially, which, let's be honest, doesn't sound very appealing for your next infection. It took a while for mold juice, later refined into penicillin, to become the world's first true antibiotic, thanks to the work of Howard Florey and Ernst Chain, who figured out how to mass produce it. But Fleming's messy lab and keen observation kicked it all off. Before penicillin, a simple scratch could kill you. Infections were a death sentence. Pneumonia, strep throat, gonorrhea. Super dangerous. Penicillin changed all that. It was a miracle drug that saved millions of lives, especially during World War II. So, next time you spill something or forget to clean up, just remember Alexander Fleming. You might be on the verge of your own world-changing, messy discovery. Or, just making a mess. Number 6 is an experiment famous, not for what it found, but for what it found. The Michelson-Morley experiment. Back in the late 19th century, physicists were pretty sure that light, like sound waves needing air or ocean waves needing water, needed some kind of medium to travel through. They called this mysterious, invisible, all-pervading substance luminiferous ether. It was supposed to be the stuff that filled all of space, allowing light from distant stars to reach us. So, Albert Michelson and Edward Morley set out to detect this ether, specifically to measure the Earth's motion through it, the ether wind. They built this incredibly precise instrument called an interferometer. Think of it like a super-sensitive racetrack for light beams. It would split a beam of light, send the two halves on perpendicular paths of equal length, and then bring them back together. If the Earth was moving through the ether, one beam should be slightly slowed down or sped up by the ether wind, causing a shift in the interference pattern when the beams recombined. They expected to see this shift, proving the ether existed. They set it up on a massive sandstone slab floating in a pool of mercury to dampen vibrations. Serious dedication to precision here, folks. But here's the kicker. They found nothing. Zilch. Nada. No matter how many times they ran the experiment, at different times a day, different seasons, the result was always the same. No detectable ether wind. It was like setting this incredibly elaborate ghost trap, expecting to catch Casper, and all you get is an empty room. This failed experiment was hugely important, because this null result was a massive puzzle. It strongly suggested that the whole idea of a stationary ether was wrong. This finding directly paved the way for a young Albert Einstein, who took this no ether idea and ran with it, leading to his theory of special relativity, which completely revolutionized our understanding of space, time, and gravity. Sometimes, not finding what you're looking for is the most important discovery of all. Alright, at number 5, we're diving deep into the atom with Ernest Rutherford and his gold foil experiment. This is a classic. Before Rutherford, The accepted model of the atom was J. Thomson's plum pudding model. Basically, a blob of positive charge with negatively charged electrons scattered throughout it, like raisins in a pudding. Sounds delicious, but scientifically, it was a bit vague. Rutherford, a no-nonsense kind of scientist, decided to test this. He wasn't going to just accept it. He wanted to it, or at least probe it. His plan was brilliant in its simplicity. Shoot tiny bullets at an atom and see what happens. His bullets were alpha particles, which are positively charged and relatively heavy. His target was a super thin sheet of gold foil, so thin that it was only a few atoms thick. He figured that if the plum pudding model was correct, these alpha particles should basically zip right through the gold foil, maybe with a tiny bit of deflection, like shooting a BB gun through a cloud of mist. He even had his assistants, Geiger and Marsden, set up a screen to detect these tiny deflections. Most of the alpha particles did exactly that. Went straight through. Boring, right? Well, hold on to your lab goggles. But then, something totally unexpected happened. About 1 in 8,000 alpha particles didn't just deflect a little. They bounced. Some even bounced almost straight back at the source. Rutherford famously said, "It was as if you had fired a 15-inch shell at a piece of tissue paper, and it came back and hit you." This was completely bonkers, according to the plum pudding model. It meant that the positive charge in an atom wasn't spread out like pudding. It was concentrated in a tiny, dense, positively charged core. The nucleus. This experiment single-handedly overturned the plum pudding model and gave us the nuclear model of the atom we know today, with a dense nucleus and mostly empty space where electrons orbit. Talk about an unexpected bullseye. Number 4 on our list is all about getting physical with energy, thanks to James Prescott Joule and his paddle wheel experiments. Back in the mid-1800s, scientists were grappling with the nature of heat. Was it a fluid-like substance called caloric that flowed from hot to cold things? Or was it something else? Joule, a brewer by trade but a physicist by passion, had a hunch that heat was related to motion or work. He wasn't just thinking about it. He decided to measure it with some ingenious, if slightly Rube Goldberg-esque contraptions. He was all about precision, a bit like Lavoisier with his scales, but Joule was weighing energy. His most famous setup involved a paddle wheel, submerged in a container of water. This paddle wheel was connected by strings and pulleys to weights. When the weights were allowed to fall, they turned the paddle wheel, which churned the water. Joule meticulously measured the distance the weights fell, the mechanical work done, and the tiny increase in the water's temperature. He did this over and over and over again, with different setups, trying to be as accurate as humanly possible. He was basically figuring out how much stirring it takes to make your bath water a tiny bit warmer, but with scientific rigor. It sounds simple, but it was incredibly painstaking work. What Joule found was a consistent, quantitative relationship between the mechanical work done and the amount of heat produced. He showed that energy wasn't being lost or created. It was just changing forms, from the potential energy of the weights to the kinetic energy of the paddle, and then to the thermal energy, or heat, of the water. This was a massive deal. It laid the groundwork for the first law of thermodynamics, the principle of conservation of energy, which states that energy can neither be created nor destroyed, only converted from one form to another. It's like energy has different outfits. Sometimes it's mechanical, sometimes it's heat, sometimes it's light, but it's always the same amount of energy underneath. Joule's experiments showed us that energy is the universe's ultimate quick change artist. Sliding into number 3 is the electrifying work of Michael Faraday. a self-taught genius who basically invented the principles behind almost everything that plugs into a wall. In the early 19th century, scientists knew about electricity and they knew about magnetism, but they were kind of like awkward cousins at a family reunion. Related, but nobody was quite sure how. Ørsted had shown that an electric current could deflect a compass needle, meaning electricity could create magnetism. Faraday, with his incredible intuition, thought, well, if electricity can make magnetism, can magnetism make electricity? It was a beautifully symmetrical question. So, Faraday started experimenting. He wasn't a fancy mathematician. He was a hands-on guy, a visual thinker. He famously wrapped 2 insulated coils of wire around an iron ring. He connected one coil to a battery and the other to a galvanometer, a device that detects electric current. When he connected or disconnected the battery to the first coil, he saw a brief flicker of current in the second coil. It wasn't a steady current, just a pulse, when the magnetic field was changing. This was electromagnetic induction. He realized that a changing magnetic field could create, or induce, an electric current. This was the aha moment that lit up the world. This discovery was monumental. It wasn't just a cool party trick. It was the key to generating electricity on a large scale. Faraday went on to build the first electric dynamo, a device that converts mechanical energy into electrical energy, and also the first electric motor, which does the reverse. Think about that. Electric generators, transformers, motors. So much of our modern technological world, from the lights in your room to the phone in your pocket, traces its lineage back to Faraday's patient tinkering with wires and magnets. He showed that electricity and magnetism weren't just cousins. They were 2 sides of the same fundamental force, electromagnetism. He got them to dance, and the world has been powered by that dance ever since. At number 2, we have Robert Millikan and his incredibly finicky but fantastically important oil drop experiment. By the early 20th century, scientists knew about electrons, thanks to J.J. Thomson, but they didn't know the exact charge of a single electron. It's like knowing cookies exist, but not knowing how much chocolate is in one chip. Millikan decided he was going to measure it, which was an incredibly ambitious task. We're talking about measuring the charge on something so tiny, it makes a dust mote look like a planet. It's like trying to weigh a single grain of pollen using a bathroom scale. You need some serious ingenuity. His setup was a masterpiece of delicate physics. He sprayed tiny droplets of oil into a chamber between 2 metal plates. These oil drops would pick up static electricity, meaning they'd gain a few extra electrons. Then, by applying a voltage across the plates, he could create an electric field that would push or pull on these charged droplets. He'd peer through a microscope, meticulously tracking a single oil drop, adjusting the voltage until the drop was perfectly suspended, balanced between the force of gravity pulling it down and the electric force pushing it up. It was like trying to juggle invisible gnats with an invisible pair of tweezers, all while doing complex calculations. By measuring the voltage needed to suspend a drop and knowing the drop's mass, which he cleverly calculated by observing how fast it fell when the electric field was off, Millikan could calculate the total charge on the drop. And here's the brilliant part. He found that the charges on the drops were always multiples of a single fundamental value. This smallest unit of charge was the charge of a single electron. His experiment not only gave a precise value for the electron's charge, but also provided strong evidence that charge is quantized. It comes in discrete packets, not a continuous smear. This was crucial for the developing atomic theory and our understanding of the fundamental nature of matter and electricity. The patience this must have taken is just astounding. And finally, at number 1, the experiment that arguably kick-started the scientific revolution itself, Galileo Galilei, and his, possibly legendary, but definitely impactful, experiments with falling objects. For nearly 2,000 years, everyone just kinda nodded along. With Aristotle, the ancient Greek philosopher, who said that heavier objects fall faster than lighter objects. It seems intuitive, right? A bowling ball drops faster than a feather. Case closed? Not for Galileo. He was all about testing things, not just accepting old wisdom. He was the original mythbuster, armed with skepticism and a desire for actual evidence. The famous story, which might be more legend than exact historical fact, but captures the spirit perfectly, is that Galileo climbed the Leaning Tower of Pisa and dropped 2 balls of different weights, say, a cannonball and a musket ball, to show they hit the ground at the same time, or very close, ignoring air resistance. Whether he did it exactly like that, or through meticulous experiments with inclined planes, which he definitely did, to slow down the motion and make it easier to measure, the point was the same. He challenged a long-held belief with actual observation and experimentation. He was saying, don't just take Aristotle's word for it. Let's see what happens. This was revolutionary because it championed the scientific method. Observe, hypothesize, experiment, conclude. Galileo's work on motion, including his studies of projectiles and inertia, laid the foundation for Newton's laws of motion and our entire understanding of classical mechanics. He showed that the language of nature was mathematics, and that through careful experimentation, we could understand its rules. It was a direct challenge to relying solely on ancient authority. So, whether it was a dramatic tower, drop, or careful ramp, rolling, Galileo's insistence on empirical evidence over dogma was a truth bomb that cleared the path for centuries of scientific discovery. It was less about the specific result and more about how he got there, by asking questions and testing the answers. That's science, baby. And there you have it, folks. 10 truly crazy, utterly groundbreaking science experiments that ripped up the rulebook and forged a new path for humanity. From decoding our very essence with the Human Genome Project, to literally playing with atomic fire under a football stadium, these moments of brilliance, and sometimes sheer luck, have fundamentally shaped our world. We saw how a messy lab led to miracle drugs, and how looking for something and finding nothing changed our understanding of the cosmos. Which one blew your mind the most? Was it Lavoisier meticulously weighing smoke, or Galileo dropping things off towers? Let me know in the comments below. I really want to hear what you guys think. These stories remind us that science isn't just about equations and lab coats. It's about curiosity, courage, and sometimes being willing to look incredibly foolish in the pursuit of knowledge. It's about challenging what we think we know and daring to ask, what if? If you loved this journey through scientific history, please give this video a thumbs up, share it with your fellow science nerds, and hit that subscribe button so you don't miss our next wild adventure. We've got so much more cool stuff to explore together, and trust me, you won't want to miss out on the next dose of mind-bending science and engineering. Seriously though, your support means the world to me, and helps this channel keep bringing you more awesome content. So, hit those buttons, spread the word, and keep that curious spirit alive. Thanks for watching, and stay curious. This is Shadow Def signing off. We'll catch you in the next one, where we'll probably build something unnecessarily complicated or blow something up. Safely, of course. Until then, keep asking questions.